Why does anything in our universe have mass? It's a question so deceptively simple that it stumped the world's most brilliant physicists for decades. If particles were massless, atoms wouldn't bind together, stars wouldn't shine, and life, as we know it, couldn't exist. Early attempts to solve this riddle ran into dead ends, leaving a glaring hole in the otherwise elegant standard model of particle physics. Then came a radical proposal in the 1960s. Perhaps an invisible field spans the entire cosmos, nudging certain particles to gain the property we call mass. This game-changing idea led to a decades-long search for the elusive Higgs boson, a journey culminating in a worldwide scientific celebration on July 4, 2012. But beneath the triumph lurked mysteries that still defy explanation. In this video, we'll explore why the Higgs boson matters, how its discovery reshaped modern physics, and why many experts believe this God particle is only the beginning of something even bigger. We'll trace the puzzle of mass, the construction of the world's most powerful particle accelerator, and the controversies that emerged once the Higgs was finally confirmed. By the end, you might wonder if we've merely scratched the surface of a much deeper cosmic plan. The Standard Model outlines the fundamental building blocks of matter, quarks, leptons, and bosons, and describes three forces: electromagnetism, the strong interaction, and the weak interaction. Photons, which carry electromagnetic force, are massless. Gluons, which carry the strong force, are massless as well. But the W and Z bosons, responsible for the weak force, are undeniably massive. How could some bosons be heavy while others are light or massless? For years, this conundrum remained unanswered. It also hinted at a deeper problem. If the Standard Model needed a missing component to explain the mass of the W and Z bosons, then perhaps it was leaving out an entire mechanism that conferred mass on other particles too. Physicists scratched their heads, tested countless ideas, and got nowhere, until a group of theorists, including Peter Higgs, offered a bold solution. Imagine the entire universe awash in a hidden energy field. Particles that interact strongly with this field move as if they're caught in molasses, and the energy needed to push them around shows up as mass. Particles that barely notice this field, like photons, remain massless and travel at light speed. This grand concept became known as the Higgs field. To show that such a field exists, scientists proposed the existence of a new particle, the Higgs boson. Think of it like a ripple in this ubiquitous field. Detecting it would confirm that the Higgs field was more than just theoretical. The only catch was nobody knew its exact mass. So building an experiment to discover it was like searching for a faint echo in a vast canyon. You know it might be there, but you're not sure exactly where, or even how loud. By the late 20th century, smaller colliders weren't enough to pin down the Higgs boson. Researchers needed more energy and far more collisions to corner such a rare particle. Thus, the Large Hadron Collider, LHC, was born at CERN on the Franco-Swiss border. This massive underground ring, 27 kilometers in circumference, accelerates protons near the speed of light and slams them together millions of times per second. The engineering feats behind the LHC were astonishing. Huge magnets, cooled by cryogenic systems, guided beams of protons along the circular tunnel. But even though it was only half the story, the two major experiments, ATLAS and CMS, each the size of a cathedral, were designed to sift through colossal volumes of data. Out of billions of collisions, only a minuscule fraction might produce a Higgs boson. On top of that, the Higgs, if created, would decay into lighter particles almost instantly. Scientists had to catch the decay footprint before it vanished in the ocean of other particle debris. After years of planning and intense data analysis, two separate teams announced they'd seen a mysterious bump at about 125 gigaelectron-volts GeV. This signal was far too statistically strong to be a fluke. The odds of a random event mimicking it were so small that scientists declared the Higgs boson had finally been found. It was a massive triumph for the Standard Model, offering the missing piece that explained how particles like the W and Z bosons gained their heft. The global physics community rejoiced. Nobel Prizes were awarded, and the media seized upon the nickname God particle. Scientists had mixed feelings about that moniker. Some found it catchy, while others saw it as misleading. Regardless of the name, the discovery completed a framework that had been built over decades. For a fleeting moment, it seemed as though we were on the verge of a truly complete theory. But that feeling didn't last. The Higgs boson's measured mass of around 125 GeV fit predictions surprisingly well. but that didn't mean it came without complications. One of the biggest puzzles is called the hierarchy problem. Theoretical arguments suggest the Higgs boson could be far heavier than what we observe. Without additional mechanisms, quantum corrections to the Higgs field might drive its mass sky-high, up to the so-called Planck scale, which is around 101910 carat 1910-19 GeV. That's a difference of 17 orders of magnitude. Physicists ask, why is the Higgs boson mass so finely tuned to hover at 125 GeV instead of skyrocketing to more extreme energies? This question isn't just an academic exercise. It signals there could be entire layers of physics beyond the standard model that we haven't uncovered yet. One of the most talked about ideas to solve the hierarchy problem is supersymmetry, SUSY. At its core, supersymmetry doubles the particle zoo, pairing each known particle with a heavier superpartner. In principle, these extra particles could cancel out the runaway mass contributions to the Higgs. SUSY became a darling of many theorists because it offers additional perks, such as a potential explanation for dark matter. A stable, electrically neutral superpartner particle might fill that elusive cosmic role, exerting gravitational pull but remaining invisible to telescopes. Initially, many assumed the LHC would find signs of these superpartners soon after discovering the Higgs. Yet years of data have revealed little to suggest their existence, not at the energies we can currently probe. This has led some critics to wonder if supersymmetry is more of a neat mathematical framework than an actual property of nature. Others argue that the superpartners might just be heavier or more elusive, requiring even larger colliders or more refined techniques to detect. Even without a supersymmetric payoff, we know the standard model can't be the ultimate word on the universe. It doesn't incorporate gravity, has no explanation for dark energy, and accounts for only about 5% of the cosmic mass energy budget. The other 95%, dark matter and dark energy, remains a colossal puzzle. Physicists hope that further scrutiny of the Higgs boson, or potential relatives it might have, could reveal pathways into that unknown territory. As the LHC continues to run, it collects more data that could reveal slight deviations from the standard model in Higgs decays or production rates. Sometimes, a tiny anomaly can spark a massive overhaul in theory. Beyond the LHC, researchers plan even more powerful machines, like the proposed Future Circular Collider, which could be 4 times larger. Others are taking a different path entirely, using ultra-precise experiments to probe possible rare decays or measure neutrinos and gravitational waves. Any unexplained blip in those arenas could link back to the Higgs field in a way we've never envisioned. The July 2012 announcement was a watershed moment, but it also raised profound questions. If the Higgs boson is the cornerstone of the standard model, then it's standing on ground that still seems shaky. Vacuum stability is another intriguing issue. The mass of the Higgs boson suggests we might be in a metastable vacuum that could, in theory, collapse under the right conditions. That sounds dire, but the timescale for such a collapse might be longer than the age of the universe. Still, it prompts philosophical debates. Are we simply fortunate to occupy a temporary bubble that allows life? Or is there a deeper principle safeguarding our reality? Then there's the question of whether multiple Higgs particles exist. Several extensions to the standard model predict a family of Higgs bosons, each heavier than the next. If any of these are out there, they could unlock new interactions and forces, potentially rewriting the story of how cosmic structures form. Some physicists even speculate about a composite Higgs, where the boson is built from smaller constituents we haven't yet detected. Such an idea would revolutionize our notion of elementary particles, indicating that everything we've labeled as fundamental might still be made of something else. At every stage, the Higgs boson leads us deeper into the unknown. It solved one riddle and exposed a dozen more. That's how science often works. Each discovery reshapes our understanding, but also reveals how much we still don't grasp. In the grand tapestry of scientific breakthroughs, the Higgs boson stands as one of the 21st century's most crowning achievements. Yet it's also a springboard for countless new questions. It proved the existence of the Higgs field, affirming decades of theoretical predictions and filling a glaring gap in the standard model. But like a signpost pointing down a long, uncharted road, it nudges us to keep going, suggesting that a much broader landscape waits just beyond the horizon. From the hierarchy problem and vacuum stability to dark matter and cosmic inflation, the Higgs boson anchors some of the deepest inquiries in physics. And while theories such as supersymmetry haven't yet panned out, the hunt is far from over. Scientists worldwide remain determined to test every corner of data, refine their instruments, and even dream of bigger colliders. Perhaps the biggest revelation is that we're only beginning to grasp how nature truly works. We could be on the cusp of a revolution in our understanding, or we could be in for years of subtle, incremental progress. Either way, the Higgs boson's discovery turned a spotlight on the mesmerizing complexity of the universe, reminding us of our capacity for ingenuity and our eagerness to venture further into the unknown. If we keep asking bold questions and building the tools to answer them, who knows what hidden truths might come to light? The God particle may have answered one ancient enigma, but it also opened the door to a far greater cosmic mystery, one that we can't help but keep exploring. Thanks for watching. Please like and subscribe if you enjoyed the video, and I'll see you on the next one.